This video is about graphs, specifically how we can use graphs in our problem solving. Okay, so I hope that you've hit graphs somewhere in your mathematical courses that you've taken. You will certainly hit it in a discrete mathematics course, something like that. But graphs and sets are probably what we use more than almost anything when it comes to computer science. So you will see them again, certainly in a networking class, maybe in other classes as well. So the book has a decent summary of this, a decent introduction. I'll go through some of the basics. Okay, so the biggest thing to remember about a graph is that when you have a graph, we'll call it G in this case, it's going to be composed of two different sets. Okay, the first set we call V is going to be a non-empty set that it contains the vertices. Okay, so the vertices are kind of the endpoints or the nodes of our graph. As we can see in our example down here, the one, the two, the three, and the four are all vertices. Okay, so this is where the information's held for the graph. And then we also have this E. Okay, so the E is a set of ordered pairs that denote all the different edges or connections between the nodes. Okay, so and when dealing with these, it's helpful, and I assume that you're familiar with basic set terminology, such as being an element of the intersection of two sets and the union, things like that. Okay. And also the idea of a subset. So in our drawing, we're going to represent each vertex by a circle. Each edge is an arrow. In this case, it's just a line. Okay. So in this graph, for example, we can say that V is equal to the set of the vertices 1, 2, 3, and 4. E is then going to be a set of the ordered pairs that denote all the edges. Okay, so we've got a 1 to 2, we've got a 1 to 3. Okay, there's a 2 to 1. Notice that 1 to 2 and 2 to 1 are not the same thing. Okay, we're going to do them both. We have a 2 to 3. Okay, there's should be, and I get this wrong every time, there should be a 3 to 1. Okay, these are a lot to keep track of. Oh, I'm in the wrong mode. Don't you love the first time I go to this mode, it doesn't do what I want. Editing mode, that's what I want. Yeah. Yeah, I've left some out here. So 3, 1 is a node, okay, or an edge. 3, 2 is an edge. 3, 4 is edge, and then finally 4, 3. Okay. So from vertex 1, I can get to 2, and I can get to 3, and so forth as we go along. Okay, so that's basically how this works. So note that in this graph, we don't have any arrowheads on our arrows. Okay, this is called an undirected graph. So we can get from 1 to 2, we can get from 2 to 1, no problem. Okay, so in some cases, we want that to be a difference. So we have a directed graph. With a directed graph, there are arrows to show which way we have. Okay, so this makes things a little more specific. So in this case, we still have our V is still the same set, but E has 1 to 2. There's no 2 to 1. In fact, from 1 to 2 is all that we have. Okay. 2 only goes to 3, so there's a 2 to 3. 3 only, 3 goes to 1, and 3 goes to 2. So 3, 1, 3, 2. And 4 goes, another typo, 4 goes to 3. Okay. So if you want it to go both directions, so in this case, we want to be able to go from 2 to 3 and 3 to 2, then we have to put in 2 edges for that. Okay. So in this particular graph, there are sometimes cases where you can't get everywhere. So if we're starting at 1, or if we're starting anywhere but 4, there's no way to get to 4. Okay, so this can show kind of how things work. Okay, so we call a graph a subgraph if it has every, so let's put it this way, every vertex in the subset is a vertex of the big graph, and same with every edge. So it's some of a graph, but not every one. Okay, but it doesn't contain anything that the main graph doesn't have. Okay. So some other terminology we can use here. We're talking about two vertices U and V are adjacent if there's an edge between them. So if they're adjacent, then the ordered pair UV is going to be an element of EG. Okay. We say that an edge is incident on the vertices U and V. Okay. If the edge is incident on only one vertex, it's called a loop. And I can't do it in my Google Drive doc here, but it would just loop back on itself. It's a circle that goes back on itself. Okay, and sometimes you do that. Okay, so if we have two edges that are associated with the same pair of vertices, like we had the 2 to 3 and 3 to 2, those are called parallel edges. Okay, so a graph is called a simple graph if it doesn't have any loops, so it doesn't have any that stay on the same vertex, and it doesn't have any of the parallel edges as well. Okay, so we talked about this idea of a path. A path will be a sequence of vertices, okay, that go from one place to the other. Okay, two vertices are called connected if there's a path between them. So it doesn't have to be an edge, but so if there's an edge, they're adjacent. But connected means you can get there from here, basically. Okay. So if we're going to represent graphs for a computer program, a couple ways to go. The first one's called an adjacency matrix. And for this, we're going to create a square matrix, which is whatever it's whatever the number of matrices. So if our number of matrices is 10, we're going to create number of vertices is 10. I'm going to create a 10 by 10 matrix. So it's a square matrix with the size being however many vertices there are. Okay. And then basically you're going to have for each vertex, you're going to have show its connections to the other vertexes. Okay. So in this example, okay, so we've gone up to this directed graph here. Okay. So we're looking at 1. What does 1 have a connection to? 1 only has a connection to 2. Okay. So I have a 1 in only the second place here. Okay. Then the 2 has a connection only to 3. Okay. So this is 2 and it goes into 3. Okay. And kind of goes from there. So that's basically how this works. So we could have this in our C++ code like this. One thing that gets confusing, the way I've numbered things, and I should have numbered it differently, we probably want to start our numbering at 0 just to make it match up, and then we're going to have a row 0. So that would have been better to have my first vertex be named 0, but you get the idea. Okay. So you can tell if there's a connection between the two. So let's say I'm at node or vertex 3. Can I get to 1? There's a 1 there. Yes, I can. Okay. So I know I can make that. Okay. The problem with this approach is as the graph gets bigger and bigger and bigger, and some of these are really big, there's a lot of practical applications to this. We're going to find ourselves storing a lot of zeros. Okay. And that can be wasteful. That's called a sparse matrix. And they take up the same amount of space whether there's anything in them or not. So we have this idea instead of this adjacency list. So with the adjacency list, it just shows where we can get to from each of the vertexes we have. And I've changed the 1, 2, 3, 4 in the code to a 0, 1, 2, and 3. Okay. So we're basically going to say for 0, which is our first vertex, we can get to 2. From 1, we can get to 3. From 2, we can get to 1 and 2. And from 3, we can get to 3, which is not correct. 3 should go. That should be the last one. 4 should go to 3. Or because I didn't make that connection, 3 should go to 2. That's what we're doing there. Okay, and nothing goes to 1. Okay, 3, which is 2, goes to 0. And 3 also goes to 1. Okay, it should go to 0. Yeah. Again, I didn't keep my numbering consistent, so that got messed up. Okay. So if we have code, again, we can use an unordered linked list to keep track of these. So we have an array of unordered linked lists here. Okay. Based on the number of vertices that we have. And then we can insert for each of these whatever number we have. So the first one, the G sub 0 just gets the inserted 2. We're inserting to the last. It doesn't really matter, but that would keep them in order. And then for 1, we're going to insert the 3, but 2, we insert 2. Okay, and that should be again a 0 and a 1. Okay, and then 3 would do 2. Okay, so this is the more common way to do things. just because it's more efficient, as linked lists are always more efficient. Okay. So there are some operations that we can create that we can do with our graphs. Okay. If we're going to, and I'm going to tell you that I'm not going to give program assignments on this. We've done a lot of programming in this class, and these get a little bit convoluted. And we'll talk a little bit about why when we get to the traversals. But they're useful. There's some code in the book you should look at, but the homework is going to be on solving these problems on paper, kind of like we did with the adjacency or with the AVL trees. Okay. So when we're doing a graph, we need to be able to create the graph. So we're going to have to use some particular graph representation. Typically, that's going to be the adjacency list. But on a small sample, we could do an adjacency matrix. Okay. We need to be able to clear the graph, to make an empty graph. We need to determine whether the graph is empty or not, a Boolean function. Traversing the graph, okay, just like we had with trees. So again, trees are not graphs and graphs are not trees. So trees don't have the ability to go round and around. I don't think I mentioned it, but the book talks about if we can get from a node to another node and then back to itself, that's called a cycle. You can't have a cycle in a tree, but you can in a graph. Okay. So the cycles become important when we're talking about traversing the graph. And printing, basically, you do a traversal as well. Okay. So with the traversals, there are two basic ways. There's a depth first and the breadth first. Okay. So the depth first is trying to move away to get as deep as possible down the layers. The book has an example that I've copied, and it's not a big enough example to make a lot of sense, but it will give us the basic idea. Okay. So for this general idea, we always start with 0 on its traversal, or the lowest number. We're going to mark that as visited. So that goes to the first one in our list here is this. Okay. We're then going to go to the adjacent vertices in order. Okay. So we start here with going to 1. That's the lowest one. Okay. 1 goes next. Since it's depth first, I'm going to go ahead and keep going as far as I can go. So I go ahead and go to the 4. So the 4 is the next. Okay. I can't go any further. The arrows are all against me here. So I have to go back to the next one I was waiting on, which is 3. So 3 comes next. 3 goes to 2, which goes to 5. Then in order, we go to 7 and we stop. We go to 8 and we stop. Okay. The things we have not visited in lowest order are 6 and then finally 9. Okay. So that's how the depth first. Again, you're trying to get as deep as possible, get away from where you start as quickly as you can. So you follow the path as long as it goes. Okay. So the other way to look at this is through a breadth first traversal. So with this one, you're going to cover everything that you can get to from where you're at, and then you move. Okay. So you cover rather than going away from it, you're going to cover all the paths as you go. Okay. So in this one, we're going to start for each vertex V, we're going to add V to a Q. And we're going to start the breadth first search at Q, or at this V that we've added to the queue, mark it as visited. We're going to then remove the vertex from the queue and then look at all the adjacent things adjacent to you, add those and keep going. Okay. So in the graph we have up here, I'll go ahead and delete this temporarily so we can see the graph while we're looking at it. Okay. So here we start at 0. Again, we want to cover everything. We do the 1 first. Again, we go in order, and then we do the 3. Okay. So we've covered those. The next one we can get to is the 4. Okay. So the 4, we can't go anywhere else. Okay. So then we go to the 2. The 2 goes to the 5. That's all it can go to. Okay. Then after the 5, we go to the 7. 7 doesn't connect to anything. Okay. And then from here, we were at 5. We went, when we were at 5, we go to 7 first, stop there, but we also go from 5 to 8. That comes in next. Okay. And then there's 6 because there's nothing else that connects. And then in the same way, there's a 9 because there's nothing else that connects. Okay. So again, rather than going away, so we don't do the 3, 2, 5, 8, we do the here and here, here, and then we do here, and then here and here. So you're trying to fan out, cover everything as you go. Okay. So we also have the ability in our graphs And this turns out to be pretty handy. That's not what I wanted to do. That's what I wanted to do. Okay. It turns out to be pretty handy to have a weighted graph or to put a number on each of the edges. Okay. So when we're doing this, it allows our graph to represent things such as distance or travel time, or in a network, the speed to transmit something across. Okay. It could be a cost factor of some sort. Okay. So in these kind of graphs, and I don't think I copied one over, but there are certainly some in the book, all of the lines will have numbers on them. Okay. So with this, okay, if we have a path from node X to node Y, then we can add up all the costs along the way, or all the weights of each of those paths. Okay, that would give us the weight of the path, the sum of all the weights of the edges that form the path. Okay, so from that we can start to do some things that make some sense in solving problems. So for example, we can figure out the shortest path. That's the path with the smallest weight. Okay, and there are lots of algorithms that you'll talk about when you get to the algorithms class for dealing with this. But it's just a way to determine if if we're using it from a map, if I'm here in Johnson City where I happen to be, if I want to go to New York City, then what is the path I can take, and what endpoints along the way that will take less time, or conversely cost the least, because there are tolls as you get further north. Okay, so that's kind of the idea. Okay, so we also have these other things with the weighted graph. The first is a spanning tree in general. So that doesn't have to do with the weighted graph, but a spanning tree is a subtree of the original tree that still has all the same vertices. Okay. So with the idea of a spanning tree, you're going to take all the vertices stay the same. You're going to remove edges that are redundant, so you can still get to everything. Okay. So everything's still connected, but you don't have the excess that you had before. Okay. But the idea of a minimum spanning tree is when you create different spanning trees, you're going to find one, sometimes it's not unique, but you're going to find one that has the lowest total cost of all of the edges that remain. Okay. And those can be useful as well. Okay. So I wish we had more time to talk more about graphs, but we are getting down to the end and we don't. So that's all we're going to be able to do. So again, there will be, look at the chapter, there will be some graph problems there. Um, it's possible I may do a video with if I get a graph program up and running, I may demo that, but I'm not sure. We'll just have to see. Okay. So this is the next to last video as far as new content goes. So the last video is going to be dealing with the standard template library. And if you didn't see my announcement from before, no homework problem up until now should include things like stack in angle brackets or queue. Those are all from the standard template library, and we're specifically not using those in this course until the very last chapter that we cover. Okay. It's not that there's anything wrong with them. It's just that we're learning how to do them on our own so we can understand them better and we can be able to customize them, which you often need to do. Okay. Instead of using the built-in ones. Okay. So that's it for this video. So one more video to go, and then there'll be a video with a review for the final exam.